Hello, good morning. Let's start with biophysical models for fMRI. Any questions? No, good. Then let's continue. So essentially we are in the process of specifying the deterministic aspect of these probabilistic models that are called in the cognitive neuroimaging neuroscience community dynamic causal models. And as discussed at some length last time, we will first focus on the deterministic, dynamical / ODE / biophysical aspects, and then we're going to talk about in more detail their embedding in a probabilistic model, a likelihood model for data, and their inversion in the second part of the term. So last time the main thing that we discussed in terms of content about DCMs for fMRI is that we specified in fairly general terms and fairly high level a function h, something like that. Actually, you can put it in the middle, a function h. And this function, which we treated as a black box and which we now want to look at in more detail, what it took was as inputs some experimental manipulations, which we called U, and which are these onsets functions that you're somewhat familiar with from GLM for fMRI. And it took parameters theta f and theta g. And what it returned, or what it returns, are separate ones, predictions for the MR signal over time in multiple regions of interest. Yeah. So we discussed a little bit also what kind of data goes into that, and I emphasized that these are multivariate models. They are actually spatial temporal models in the real sense of the word spatial temporal model, not in the RSA sense of the word. And these are the regions. So this would be first, so the prediction for the first region of interest, second region of interest, and third region of interest. And this is what this function h somehow does. And that's kind of the very big picture view. And this is purely deterministic, as I also said. So if you put in onset functions that don't have any driving inputs, don't have any sticks, which are not onset functions then, but just constant zeros, the prediction for all these regions of interest will also be a flat line. How many regions of interest there are, how many condition onsets there are, that's fairly flexible. That depends on what you want to model. Good questions about this at this point? No. Good. Then the topic today is to obviously look more into this black box H here, and again start looking into that from a kind of big picture aspect. And once we've done that, then we zoom in even further, and then the real biological and physical aspects will get ever clearer. But for now, we zoom in a way into some kind of meso level. So we are now at a fairly macro level. Now we zoom into a meso level that emphasizes the ODE aspects and dynamic systems aspect. And then we later, after we've done that, we zoom into the micro level where then the kind of biological aspects get perhaps clearest. Good. So so we're talking now about this function h, which takes input functions, parameters, and returns predictions for MR series of regions of interest. And the standard formulation of that that you also find in DCM tutorials and the DCM papers for that looks as follows. You have some state vector x, and what is specified is the rate of change of this state vector x as a function of the inputs and the latent parameters theta f, and this is what also then one would refer to as the latent level, because this is not directly observed. It's unobservable level, if you want. And another level that one can call observation function. For example, that maps the state variables of the latent level onto some predicted MR series. MR series again for the regions of interest. So this is multivariate, real MR series for regions of interest. Royce. And in high temporal resolution, so in for time that is modeled by the real numbers, and which we can colloquially refer to as in high temporal resolution. So what the function h then, in addition to somehow, so if you think about our function h, it delivers, how do we do that? So it delivers the u and the theta f to this function f. It delivers the theta g to this function g, and then these things do something, and then z comes out, and then the function h. So here, this is what h does. No, this h, whatever. And what then the function h also does is that it takes this z and downsamples it, and it does something else which I know forget. So it definitely downsamples it, and makes it really then amenable to act as the data prediction, not as some high temporal resolution MR time series, but as a data prediction for the data that was actually acquired, namely the MR data. Yeah, and obviously today we want to talk about this aspect. So in a way, these kind of two-level models, where one, especially the latent level, is defined in terms of a differential equation, and then there's an observation function, which is here the g function, that takes the latent stuff and maps it to the observable level. In general, these models are also called state space models. Just a second. State space models. Usually, and there is where you have to pay attention, often when state space models are being used, then there are some random contributions. Here right now we don't have any random contributions because we're taking the Z as a deterministic prediction. Only after then putting it into the Gaussian likelihood function there will be some observation noise. But this two-level description for models, that's a very common thing. Yeah, so you will find that a lot in the neuroimaging literature, and it's also closely related to things like hidden Markov models, Kalman filters, Bayesian filtering, and so on. So that's a very common pattern or motif, and yeah, you see it for the first time here today. Now that we have that, we will look at all these constituents of this in more detail. But first, we have a question.
Yeah, I didn't quite understand how we get the u theta f and theta g from the h function, because I thought that is only at the input to the h function.
Yeah. So essentially, what it's actually, so this, do you see this circle here in this thing? That's this circle. We are looking into the h function right now. And the h function, as input, it gets this. And because the h function gets this as input, and this is the h function, it also gets this as input. Yeah. So the h function doesn't deliver something to something else, but this is the h function. But the h function does also more things. It also downsamples the data. Yeah.
I have a question. The x, you said it's a state vector.
Yeah.
Referring to the state of where am I?
Yeah. So what all these things are, we will talk about now. Yeah.
So z comes not as a result of h function.
No, that is actually part. No, not quite. So you're right. So z is kind of an intermediate result in the h function. So it's somewhere here, let's say, and then it needs to be downsampled, and then there's a result of the thing. Yeah. Good, but then the next thing is to discuss what these XF and stuff now are. Yeah? Questions? More questions? No. Good. Good. So that's now in a way, and if you look into DCM, for example, these new DCM tutorials by Peter Zeitman, this is a typical thing that you always find in terms of DCM. Sometimes a little bit different to what I describe here in terms of the details, because it's usually a little bit wrong with regards to the actual implementation, but it has this two-layer structure. Question is now, what are these things? And this is what we're going to talk about. So the U, let's, I don't know, put it like this, constituents. The U has not changed. That's or there's also not much to talk about with respect to the U. The U is still this univariate vector valued function that takes time as an input and returns a vector of condition onsets. This is exactly the same as we did last time. So NC, just to get that clear, NR is still number of regions, and C is number of conditions or experimental event types, however you want to call that. And U has not changed, yeah, so that's still what it is. New things are obviously the X, the F, and the G, and in a way also the Z. Theta F and theta G we've also seen previously, and we will talk more now in detail, but we start with the X. So what is x in this context. That's what is always then in these kind of models referred to as the state. Doesn't mean anything, so it doesn't. So also the question. So state is just a very generic term for things that can describe whatever. Usually states. That depends. It's just called states. It doesn't really make sense to, at this point to talk more about why it's called states. We will see what is meant by that in real detail in a second, or not quite, maybe only next time. But this is called the state, and what it really is a function. So it's time dependent for each time point. There is a value of the function s, and this value of the function is ns dimensional, and ns is the number of states, or of state variables. And what these state variables are, as I said, we will discuss. It's also, you should, it's the function here with the f. So that's x dot equals some function of x and some other things. That's of course what you've already familiar with in terms of ODE systems. Yeah, so that's nothing new. That's the rate of change of this vector. Remember, that means that it's the rate of change of each state variable is given as some function of its current state. And in this case, some input functions and some parameters. Yeah, but it's exactly, so it's basically building on what you have learned about ODE systems, and it's also in analogy, of course, to what you learned about the MR model. Yeah, it's in terms of kind of the model class. This is, yeah, it's essentially the same as the MR model that we discussed in the second half of last term. There's a little bit of a difference, that there's some what one would call driving input, so this U, so it's externally driven and modulated, but in terms of the things that are important, so that you know that it specifies the rate of change of something. If you want to see what's actually happening, you have to integrate it. You need an initial condition, and you can either analytically integrate it or you can do that numerically. This is all the same. And what it then what you then get if you have an initial condition and you integrate the whole thing, then you have a multivariate ns dimensional time series, and for each point in time you get this state vector, and the important thing is that this is a function of time all the time. So this means that we can talk about f in a little bit more detail already. So f, so this function f that I specified, what it takes as inputs is an ns dimensional vector, namely the vector or the value of x at time t. It takes an NC, so number of condition vector at time t. So that's the input functions, which also vary over time, and it takes an element of this parameter space, and what it returns is an ns dimensional vector. Yeah, so that's I mean, it's immediately clear once I specified what x is, then it's also clear what f is, because you know all the other things. So it's not really some new information, just some basic writing down things. So this function f takes this ns dimensional vector, the nc dimensional vector u, the parameter values theta f, and what it returns is the rate of change of x. Yeah. So again, remember what this x dot means is that you have ns, so number of states, univariate real-valued functions here. So it's one big vector of rates of change at a given time. Yeah. Good. And of course, we need to specify the functional form of that. Before we do that, just briefly, what the function g then does. So this is also, this is why I'm doing this here. This is also called the evolution function. Of course, for the latent state. And then there's the observation function, which is also immediately clear from what we've did above. So this function g takes an ns dimensional vector, takes a value in the space of parameters for itself, namely these theta g. What it returns is a number of region dimensional vector. Yeah, so this is the predicted MR time series in high temporal resolution, and that's multivariate, but it's multivariate in number of regions, not in number of states. Yeah, so that's important. So it's essentially what you will see is that there are many more states than there are regions. In fact, there are 5 states for each region. We will look at that. It basically, you can also view it as projecting a high dimensional latent model onto then lower dimensional but still multivariate data features. So it takes a state vector of dimensionality ns, takes a parameter vector theta g, and maps it onto a value of it, and this value, as seen above, we call z. And again, always keep in mind that all of this is time dependent. Yeah, so z for each point in time, z is an r dimensional vector, but for the next time point, it's still an r dimensional vector, but the values might have changed. Yeah. So these are the important things, the evolution function and the observation function, which is of course fairly implicit already. If you see this, it doesn't add much in terms of content, only that we now specified a little bit more the dimensionalities of things. Questions up to here? Good, that doesn't seem to be the case. Then we can zoom in even further and now first talk about the evolution function in more detail. So the evolution function is interesting. What the evolution function does is that it, in terms of how it's designed, it partitions regions of interest wise. So if you say you want to model the data from 3 regions of interest or 5 regions of interest or as many voxels as there are in your data acquisition regions of interest, then you specify as many regional specific evolution functions. So the way it looks, we've seen that above. So it takes this NS-dimensional state vector, the input function vector, the parameter vector returns the rate of change of the state vector. But now the way it looks in a little bit more detail is as follows. In fact, what you find is that it consists of NR functions that are all really, really similar. So they are actually the same functions. Oops. I had this way to that. Like this. And each of these regional specific functions takes in the entire state vector, because the entire state vector and the entire condition function vector and the parameter vector, although it might not, or each of these sub-functions might not require everything in there. Yeah. So the thing is, it partitions source-wise. Now the question, so not source-wise. I always say, I just said source-wise because it's in analogy to EEG, where things partition source-wise. Here things partition region of interest-wise. And then the real question is, how does each of these Fi now look? Because so far we've just been doing things on a fairly abstract level. If you think about programming, we've just say there's a function that takes this high-dimensional input and gives that a high-dimensional output, but we never said what's actually happening inside the function for real, and now we're saying it. So there are these functions Fi, and they take in the entire state vector, the entire onset vector, the parameters, and what they return is a 5-dimensional thing. And this 5-dimensional thing is the state vector for each region. Yeah, and we call that xi in R5. That's the state vector for a region of interest I. Yeah. And I is, of course, 1, 2 number of regions. So again, if you decide you want to model the data from the visual area, V1, the visual area TE, the interparietal sulcus, and the frontal cortex, then you have 4 regions of interest. What the DCM framework and the model that's used here then implies is that you assume for each of these regions, you assume 5 state variables. And these 5 state variables have now biological meaning. And this is what we're looking at now. So the first state variable in each region is a neural state. So these individual state variables, they are univariate real-valued functions. Yeah, so that means that x I, that's a function from the real numbers to the real numbers. And for each time point, what it returns is a real number. And in DCM, this real number then models the evolution of the neural state of that region. Yeah. So if the question comes up, what is neural activity in DCM? That's one real number that evolves over time. Yeah. As I said, this has, or I don't know whether I said it, but this has been generalized to also doing here some kind of population, neural population models with multiple neural state variables and so on. That was only in 2017 by Carl Friston again. If you look at the literature and the DCMs being used, these are of course the DCMs being used that are implemented in SBM forever, and the standard version. So what everybody uses is this with one neural state variable per region. Yeah. So for each point in time, the model assumes that there is one value in each of these 4 regions that I just mentioned, and that's the neural state, and this neural state can go up and down. That's the first state variable in each region, and then there are, of course, how many more? 4, thank you. Interactive student participation. So there are 4 more, and they are number 2, 3, 4, 5, because it was implemented in MATLAB. It doesn't start with x0. And these are hemodynamic state variables. All of them, yeah. So this, in a way, shows the origin of DCM as being derived from biophysical models, especially models for neurovascular coupling and hemodynamics. So these let's call them XJ, they are of course also univariate real valued functions, and reflect certain, oops, this goes, that's better. They reflect certain hemodynamic variables, which we will also talk about in more depth. And there are 4 for each region. And for some reason, in the people who promote the use of DCM via SBM, it's a little bit hard to get from them what's going on with these hemodynamic variables. That's always a little bit unclear. But the so the whole the state vector. Yeah, maybe let's come to the state vector. The state vector then of the entire model comprises 5 state variables per region, and depending on how many regions you then want to model, it comprises 5 times number of regions state variables. Yeah. So if you for example have this thing with these 4 regions of interest that I briefly mentioned, then you have 20 state variables. Good. So then let's have a look at how this fi function then looks in detail, and this is also then in a way giving us the task then for the remaining sections on this DCM model, because we'll have to talk about what that means. So each of these fi functions takes as the entire state vector, the input function vector parameters, which we will now also see, and returns a 5-dimensional entity, which is the rate of change of the state variables of the ith region. Yeah, because these are evolution functions, they return the rate of change, and it's 5-dimensional, and it specifies the rate of change of the neural state variable and of the hemodynamic state variables 2, 3, 4, and 5. Yeah, or the 4 hemodynamic state variables. So how does it look like? So if you have the script in front of you, there's actually a bit of typo mess in terms of the first state variable. So hope I write it now correctly. We will talk about it anyway, and we will go back and check. The remaining ones are, I think, fairly okay. So the rate of change of the first state variable, which is the neural state variable, is specified, and now don't look into the script, it's specified in this way. So it actually looks at the current state of the neural state variable in all regions, and the regions are here indexed J. So it looks into the neural state variable in regions J, 1, 2, 3, 4, how many regions you have, including itself, yeah, and multiplies this state with some parameter values A, I, G. It also looks at the input functions and multiplies these with parameters B, I, J, K. And somehow lets these interact with the neural states of all regions. Again, this is X1. And then it also looks into, actually we might write it as, do we? I don't know. Maybe we do. It also, that's wrong, it again looks at the input function here and multiplies these with parameters CIK. That's about the neural state. Yeah? What this means and how this relates to effective connectivity and how this is usually formulated in terms of DCMs, we will all talk about. Yeah? The important thing, what I'm trying to stress here, is that it's an explicit formula that for the rate of change of the neural state in the ith regions looks at all neural state variables across all regions. It looks at the input functions and it somehow creates some form of interaction between input and neural states. Yeah? So maybe, yeah. Just keep that in mind. We will look at the details of that again, because we have to. And then there are 4 more formulas that I essentially just write up right now, looking a little bit into at least their structure. For the hemodynamic states, and again we will look at this in some detail. What you also find there is, I will talk about this in a second. So that's for the first hemodynamic state. What you see here is that the first hemodynamic state is affected, of the ith region, is affected by the neural state of the ith region. Yeah? So you have some coupling between the neural state and the hemodynamic states, because the rate of change of the first hemodynamic state, which is the second state of the 5 states in each region, the rate of change of this hemodynamic state is dependent on the neural state. It is also dependent on some parameters, kappa, and what I also introduced here is that to make things work on the side of the evolution function, there is some exponentiation of the state variables, and to have the description a little bit leaner and not too many exponentials in there, I defined this tilde variables, which are the exponentials of x of the respective state variables. The exponential function here just serves to make things that are negative positive. Yeah? So if you think about the exponential function, you of course think about this graph that is kind of exponentially increasing. But the important thing for this here is that on the negative, for the negative inputs, it also always has a positive output, and this is why this is done here, because these things need positives, need to be constrained for positive numbers. So that's the first hemodynamic state variable. The second hemodynamic state variable is given by this. So for the moment, just in your mind say, for all of these complicated equations, or think simple equations, whatever you want, but just think equations and don't think about them, because we haven't talked about them yet. So these are just equations that have meaning and that model certain aspects, but to go into their meaning we need time, and currently we are just seeing them for the first time and appreciate that these are equations and or formulas, and that's awesome, but we don't associate anything with them. One thing that is of course also interesting, or that one also, what this writing this up also helps with, is of course to appreciate, okay, this I need to understand and nothing else, because this is then, one understands these 5 evolution equations on the latent state for the latent system, then one has understood what's going on, and there is nothing else that one has to worry about. Yeah. So these are so this is the rate of change of x1, rate of change of x2, rate of change of x3, rate of change of x4 and x5 for the ith region, and I'm concatenating this now. Let's get rid of this. And that's essentially it. So again, maybe I put it next to it. So this is dot x1i, this is dot x2i, this is dot x3i, dot x4i, and dot x5i. So you see that, of course, these 4 here, this, and this, are hemodynamic states, and this is where the whole thing originated. Yeah. So what you have here, so these things, this is the essentially that's the balloon model that was proposed in the late 90s, and then what happened in the proposal for dynamic causal modeling in the early 2000s was to augment this with this neural state thing here, and then also have it for multiple regions. Before we take a break, let's just briefly then, based on this, concatenate the parameters. So what is theta f? Well, theta f is the set of all these parameters that are in there. They're a, I, j, where I and j, Python style, go from 1 to number of regions. The b, I, j, k, where b, I, j, k, I, j go from, where I, j again go from 1 to number of regions, and k goes from 1 to number of conditions. And then we have the c, I, k with the same index meanings, and then we have so these are all, of course, for the neural state evolution, and then we have parameters that apply to the hemodynamic states, namely kappa I, f, which is there, kappa I, s, which is there, some tau 0, don't know what that is at this point there, some alpha I, is there, and some at E0, and I hope I didn't forget one. And these are all real numbers. So we also now know what theta f is, at least in terms of its scope, the numbers that play a role. We don't know about the specific meanings of these yet, but we will get there. Yeah? Questions right now? No. Good, then let's have a break, and after the break do the same thing for the observation function, which you will see is already less complex. So I think the most complex thing that sounds like daunting and makes you want to think whether you really want to be a cognitive neuroscientist or everything is just too confusing of the whole thing is actually this, but we will go about each of these step by step, and then you will see it's not complicated at all, and it's awesome to be a computational cognitive neuroscientist. Good, so let's have a break and start again at 9.